Welcome to This Explainer. Today, we're putting on our analytical hats and diving deep into a topic that honestly usually stays pretty well hidden behind industrial gates. We're going to break down exactly how to quantify the massive, almost unbelievable water appetite of oil and gas refineries. To do this, we'll be using the official Sustainability Accounting Standards Board, or SASB metrics. Specifically, we'll be exploring the standard coded as EM/RM 140A.1. Think of this explainer as your masterclass in decoding environmental risk, taking you directly from the raw dry standards to actual real-world application.
To start us off, I want you to put yourself right in the shoes of a risk analyst. Imagine you're evaluating a massive refining facility. The pipes are humming, the cooling towers are steaming, and millions of gallons of liquids are flowing through the system every single day. Your task? To launch an active, rigorous investigation into this facility's environmental footprint. The core question where we absolutely must begin is this: how exactly do you measure a refinery's thirst? Because, as you'll see, it's not just a simple matter of looking at a monthly water bill, it's a highly specific, complex accounting process.
But before we can start measuring anything, we have to precisely define our terms. And the SASB standards give us a really fascinating technical baseline to work with: 1,000 parts per million. According to regulatory guidelines, water is only strictly defined as freshwater if it has less than 1,000 parts per million of dissolved solids. If there happens to be no local legal definition where a particular refinery operates, well, this is the exact benchmark we use to evaluate whether a facility is tapping into critical freshwater reserves.
Okay, let's dive into our roadmap for today. We'll outline the refining water challenge, make a critical distinction between water withdrawn versus consumed, define baseline water stress, get into the exact math of calculating the stress percentage, and finally, discuss why these metrics matter.
Let's kick off with Section 1, the Refining Water Challenge: Size, Complexity, and Risk. When we look at a refinery, its overall water risk depends heavily on its sheer size and the immense complexity of its processes. Different types of crude oil inputs and specific product requirements need vastly different treatments, and that drastically changes the intensity of the facility's water usage. Extracting these huge volumes of water introduces severe risks. We're looking at potential exposure to escalating water scarcity costs. We see heightened, sometimes intense tensions with local communities over shared natural resources. There's an incredible need for complex on-site wastewater treatment before anything can even think about being safely discharged. And looming over all of this, for sure, is the constant threat of regulatory disruptions. Water isn't just an operational input here, it's a critical threat vector to the entire bottom line.
Which brings us to Section 2, withdrawn versus consumed. This is a critical distinction.
Now, what's really interesting about this is that we basically need to act like forensic accountants, because not all water is treated equally on the balance sheet. Comparing the two categories, total water withdrawn includes every single drop pulled from the environment. We're talking surface water, groundwater, collected rainwater, and municipal supplies. But total water consumed is a much stricter, way more permanent category. It only counts water that is evaporated, directly incorporated into the actual petroleum product, or moved to an entirely different catchment area. So, water that just passes through a cooling system and goes right back to its local source, that's withdrawn, yeah, but it is not technically consumed.
That last point definitely requires a closer look. Catchment relocation is officially defined as water that does not return to the same catchment area from which it was withdrawn. So the absolutely crucial point is this: if a refinery pulls fresh water from a local inland river, uses it, treats it, and then pumps it out into the sea, the standard explicitly counts that water as consumed. Why? Because as far as the local inland ecosystem and the surrounding community are concerned, that fresh water is permanently gone.
Now we shift our focus from what is happening to the water to where it is happening in Section 3, defining baseline water stress. In the world of sustainability accounting, location literally changes everything. Think about it. 1 million gallons of water withdrawn in a rainy, flood-prone region carries a vastly different risk profile than 1 million gallons sucked out of a drought-stricken desert. To quantify this geographic risk, the SASB standards, which are now under the stewardship of the IFRS Foundation, demand rigorous geographic analysis. Companies can't just guess at their local water security. They're absolutely required to systematically analyze their global operations against recognized, standardized water risk databases to figure out exactly how stressed their operating environments really are.
Specifically, the standard mandates the use of the World Resources Institute's aqueduct tool. It's a real game changer. High baseline water stress designates a region where 40 to 80% of the available water is already being withdrawn by local agriculture, industry, and municipalities. Extremely high baseline water stress means more than 80% is spoken for. If a refinery operates in these zones, every single drop they pull counts double in terms of operational risk.
Let's move to Section 4 and see how this all builds together. Calculating the stress percentage. It's time for the math behind the metric.
This right here is the analytical core of our explainer. Here is the step-by-step masterclass for producing a standardized, comparable metric. Step 1. You quantify the total volume of water withdrawn and the total volume consumed across the entire company. And importantly, this is absolutely crucial, the standard dictates this must be strictly measured in thousands of cubic meters. Not gallons, not barrels, thousands of cubic meters. Step 2. You cross-reference your operating locations with the WRI's aqueduct tool to find out which specific facilities sit in those stressed regions we just talked about. Step 3. You calculate the exact percentage of these activities occurring in regions with high or extremely high baseline water stress. You do this by simply dividing the volume of water used in those stressed regions by your total overall volume. So the numerator is your stressed water, the denominator is your total water, again, in thousands of cubic meters.
And this brilliantly illustrates what that calculation actually looks like in practice. Imagine a hypothetical refinery's total water consumed. We have 65% sitting relatively safely in non-stressed areas. Okay, fine. But then we have 20% located in high-stress zones and 15% in extremely high-stress zones. Understanding this breakdown immediately exposes the reality that 35% of this refinery's water consumption is highly vulnerable to scarcity. For an analyst, this is a glaring red flag that clearly and instantly maps out environmental liability.
Which brings us to our final section, why these metrics matter, looking beyond the numbers. So what does this all mean? Why exactly do investors, regulators, and environmental analysts demand this granular level of transparency? Well, it essentially comes down to turning risk into operational reward. The challenge of water scarcity and community tension is met with a strategic response, implementing aggressive water recycling and targeted consumption reduction programs. And the reward? When entities actively manage this issue intelligently, they capture massive operational efficiencies and significantly mitigate their long-term costs. It proves that excellent environmental accounting drives excellent business strategy.
In fact, the SASB standard itself puts the justification perfectly. It states, reducing water use and contamination could minimize regulatory water supply shortages and community-related disruptions on operations. That is the fundamental bottom line here. This isn't just some theoretical environmental exercise. Tracking these exact metrics in thousands of cubic meters is directly tied to preventing catastrophic operational shutdowns. Because let's face it, if the water stops flowing, the oil stops refining.
I want to leave you with this final kind of provocative thought to consider. If a refinery's water stress percentage, that exact math we just calculated, keeps rising year after year in extremely high-stress regions, at what point does its social license to operate simply evaporate? When does the surrounding community finally look at the drying riverbeds and say, no more? Thank you so much for joining me for this explainer. Keep analyzing the data, keep questioning the metrics, and I'll see you next time.